Hey everybody. So today we're going to do your test one review. Let me share my screen. Here we go. Okay, here we go. Okay, test one review. So let's talk logistics first. So we're going to have our test on Thursday, September 21st. And always when you're taking a test, you have to make sure that the person that is grading it can read it. So please write legibly and write your stuff in a linear, logical fashion so that I can follow what you've done. Because if I can't read it and figure it out, it's really hard to grade it. Now, you don't have to show every step of your math, but the more work that you show, the more partial credit I can give if you make a mistake. And so at the very minimum, you have to show me that you know what equation you're using and put numbers into the equation if that's appropriate. Don't leave off units, don't leave off vector signs and notation. And if you don't do at least this much work, you're going to get points off even if your answer is correct. I really care a lot less about what your numbers are than I care about the logic that led you to get that answer. Also, if your answer doesn't have the right units or the right notation or they're not shown, then I'm going to deduct points for that. Remember that we spent a day in class talking about the grading scale for the homework and the tests. So we're going to have 10 points per, part A, B, C, D. It's going to be, all are going to be worth 10 points each part. And you'll get those 10 points if your answer is completely correct, including the notation and the units. Now, if you screw up just a little bit and you don't have more than, say, 2 unit or notation errors, or let's just say you're off by a minus sign or a factor of 2 or something, then that's one thing. You get 9 out of 10 points for that. Maybe you plug numbers into the calculator incorrectly, but it was right when you wrote it down on the test. That's the kind of thing I take off 1 point for. But if your answer is correct, your numerical and everything is right about it, but you did terribly on your units and your notation, you didn't put vector signs, you screwed up a lot of stuff along the way, I'm still not going to give you full credit. That's 8 points out of 10. Now, if you did mostly okay, you set the problem up well, and everything was okay with your concepts, but you made some math mistakes along the way, multiple math mistakes, not just a factor of 2 or a minus sign, but multiple math mistakes, then that's 7 points. 5 points out of 10 is it's okay. Your attempt was generally correct, like you started off on the right path, but you didn't finish it, or your math mistakes were really pretty bad, or you made a small conceptual error after your start, which was generally conceptually correct. Then that's 5 points. 3 points, you tried, okay? But it's conceptually incorrect, like you used the wrong formula or applied the wrong theory, or you started it kind of, but not really, and you didn't finish it. Or you made an attempt, but I have absolutely no idea what it is because I can't read it. It's illegible and it's written all over the page in some sort of crazy fashion that I can't follow. And then 0, of course, is you didn't try. Okay, so that's the grading scale. Now, in general, this test is on chapters 1 through 3 of your Matter and Interactions textbooks. I do expect you to be reading the textbook, and sections of the textbook where the lectures are covered are noted underneath the links to the online lectures. So you should be able to see that. Remember that I'm not testing you on your VPython skills. I'm testing you on your written physics skills on tests. And your VPython is just for the VPython homeworks. You want to bring a 3x5, 3-inch by 5-inch index card to the test as an equation sheet. You're not allowed a larger equation sheet than that. You can write on the front and back, I don't care, but it's 3 inches by 5 inches. I'm going to give you fundamental constants, so I wouldn't waste my note card space on that. I'll give you G is 6.673 times 10 to minus 11 in SI units, for example. Big G is that. I'm going to give you that kind of thing, so don't waste your note card space on that. If you need a conversion from inches to centimeters, I'll give you the conversion. That's fine. But I'm not going to give you those SI powers of 10 prefixes, okay? So I'm not going to tell you that a kilometer is 1,000 meters. I expect you to memorize that, okay? So while I'll give you the conversion between English and SI units, an inch is 2.54 centimeters, I'll tell you that. I'm not going to tell you that a centimeter is 0.01 meters. No, you're expected to know that at this point, and you should memorize those. If you need some help with that, here's the slide, okay? Now, I don't expect you to memorize all the way to yada. I'm not sure I even could rattle off the top of my head what zeta is, probably not. But I do expect you to know between giga, which is 10 to the 9, and nano, which is 10 to the minus 9. Okay, I expect you to know those SI prefixes. All right, I told you I'm going to be a little hard on you about the notation. The notation has to be right. So what is the notation? Here it is. Remember that one of the first things we covered was the idea of a vector. A vector is something that has both a direction and a magnitude. The way that we show a vector is by putting an arrow over the top of the symbol. So a position vector, for example, is often symbolized with an R. So an R with an arrow over the top is a position vector. Now, you can use two kinds of notation to give the components of vector, and either one of these two kinds is acceptable. You can use the triangular bracket notation and then list the components with commas between them for the X, Y, and Z components respectively. If you're going to do it that way, then you could even be a little lazy and put your units on the outside of the brackets. And that way, you know that, components are 1.5 meters, 2.7 meters, and 9.3 meters for your position vector. All right. Another way to do it is to use the unit vector notation. For the unit vector notation, we use I hat, j hat, and k hat for the unit vectors that point in the x, y, and z directions respectively. Okay, and so if you do that, then it would be 1.5 meters I hat plus 2.7 meters j hat plus 9.3 meters k hat. That's also correct vector notation. Either one of those two is acceptable. So remember that unit vectors in general have magnitude 1. Okay, so they have magnitude 1. Also remember that in general, unit vectors are dimensionless, okay? Unit vectors are dimensionless. So I hat, j hat, and k hat have components 1, 0, 0, 0, 1, 0, and 0, 0, 1, respectively, all right? Position vectors, by the way, always point from the origin to the position. So that's the definition that we'll use for position vectors. Remember that a position vector is not the same thing as a displacement vector, okay? All right, magnitude of a vector in 3 dimensions. So we are in intermediate physics concentrating on 3D vectors, not 2D like you might have seen in your 1000 level physics classes. So to find the magnitude of a 3-dimensional vector, you do the square root of the sum of the squares of the components. So for example, if x, y, and z are the components of my R vector, it would be equal to the square root of x squared plus y squared plus z squared. If you see notation like this, where you have absolute value signs on either side of a vector, that means to take the magnitude of the vector. Okay, so that's the notation associated with that. Alternatively, sometimes if you just write R, for example, with no arrow over the top, that can also mean the magnitude of the vector R. Okay, remember, if you don't have that arrow over the top, it's not a vector. Okay, it's a scalar. So you've got to be good about your notation. Now, we also discussed unit vectors for arbitrary vectors, okay? A vector that points in some random direction, not our I hat, j hat, and k hat vectors, but other random unit vectors. To find the unit vector associated with any vector, you take the vector and divide it by its magnitude. So for example, r hat, the vector that points in the direction of r but with length 1, is the vector r divided by its magnitude. So x divided by the square root of x squared plus y squared plus z squared in the x direction, I hat, y divided by the square root of the sum of the squares, j hat, and then plus z divided by the square root of the sum of the squares, k hat. So that's how to find a unit vector for an arbitrary vector. Okay, now remember that your unit vector components for your random unit vector are also your direction cosines. So r hat could be written as cosine theta x I hat plus cosine theta y j hat plus cosine theta z k hat. So when you've found your unit vector, you have found your direction cosines. If you were to take the inverse cosine of your unit vector components, then what you would find is the angles that the unit vector makes with the x, y, and z axes respectively. Okay, so theta x, theta y, and theta z are the angles that that vector makes with the x, y, and z axes respectively. And these are the direction cosines. Okay. All right, we talked about position vectors, which are the vectors that point from the origin to the position. So now let's talk about displacement vectors. Displacement of an object is defined as the change in position. So what you do is you take, if an object has moved, the final position vector and subtract off the initial position vector to find the displacement vector, which is often symbolized by delta R. Okay, so that's a displacement. Remember that the displacement is only dependent upon the initial and final positions, not the path. So if you run in a circle and you start and end at the same point in the circle, then your displacement is 0. Now that's different from the distance that you've traveled, which would be the circumference of the circle. Okay, so those two things, displacement and distance, are very different. Now we define our average velocity as the ratio of the displacement per unit time that it took for the displacement to occur. So your average velocity is delta R over delta T. From this, you can rearrange, multiply both sides by delta T, and then delta R is, of course, R final minus R initial. And from that, you can get the position update equation. And this is what we use in VPython. Okay, so R final is equal to R initial plus V average times delta T. Okay, so that's the position update equation. And it works great if you're simulating motion over small time intervals. Now, if you take that time interval delta T and shrink it down to a tiny little infinitesimal amount, then basically you're taking the limit of delta R over delta T, and that's the derivative dr dt. This is known as the instantaneous velocity. V is equal to dr dt. Average acceleration, A average, is delta V over delta T, or V final minus V initial over delta T. You can take your instantaneous acceleration the same way by shrinking that delta T down to a small little amount, and then the limit of delta V over that tiny little delta T is dv dt. Okay, so your instantaneous acceleration is dv dt. So this is how the displacement, velocity, and the acceleration are related to one another. We define the momentum. Okay, the momentum of an object, symbolized by the letter P, is equal to m times v, where m is your mass and v is your velocity. So P is equal to mv. Momentum is a vector, okay? Now forces, or pushes or pulls, the SI unit of the force is the Newton, and the gravitational force here on Earth is F is equal to mg, where g is 9.8 meters per second squared down, okay? We covered Newton's laws. Okay, so here they are all summarized in one slide. Newton's first law says that unless acted upon by an external force, objects in motion will stay in motion and objects at rest will stay at rest. Newton's second law can be written a couple of different ways. Assuming the mass is constant, then you can say that the sum of the forces, or the net force acting on an object, is equal to that constant mass times the acceleration a, okay? Now, in differential form, F is equal to dp dt, or the net force is equal to dp dt. And this is the way that Newton wrote it. The time rate of change of the momentum is equal to the force. So Newton's third law says that whenever one object exerts a force on a second object, the second exerts an equal force in the opposite direction on the first, or action-reaction is a shorthand way of saying that, okay? Now, if you were to write that one out mathematically, it's the force on 1 by 2 is equal to the negative force on 2 by 1. In other words, if I punch my hand, right, with one hand, then this hand also exerts a force back on my fist, okay? And you can feel that in both the hand and the fist, right? So that makes sense. Talking a little bit more about mass. Mass is an inherent property of an object. It's independent of that object's surroundings. It's independent of the method used to measure it, and it's a scalar. Okay, so it's not a vector quantity, it's a scalar quantity. The SI unit of mass is the kilogram, and it's important to remember that mass and weight are not the same thing. Mass is m, and weight here on planet Earth is mg, right? The pull of gravity on the object is the weight, whereas mass is the inherent property of the object. If you were to change planets or go into far outer space, then you wouldn't have any weight, for example, if you were in far outer space, but you would still have mass. Okay, we covered the kinematics equations. Remember that the main assumption for the kinematics equations is that they're only valid for situations in which the acceleration is a constant. So it's not going to be the case, for example, for spring force, where the acceleration of the object attached to the spring depends on how far the spring is stretched or compressed. Okay, so it's a different situation there. So it's only valid for constant acceleration situations. We have three kinematics equations in one dimension. So here we go. V final squared is equal to V initial squared plus 2A delta X. This is assuming the direction is X. Of course, it's equally valid in the Y direction, but the directions are independent of one another. Remember that. Also, next one, the displacement in the X direction, delta X, is equal to V initial in the X times T plus 1/2 AX T squared. So that's another one. And finally, Vx is equal to Vix plus Ax times t. So the final velocity is equal to the initial velocity plus the acceleration times the time. All right. This is also the definition of average velocity for a constant acceleration situation. Now, remember that in projectile motion, where you have an object, you give it a shoot or an initial throw or something like that, and then it's traveling through the air underneath only the acceleration due to gravity. So that's the only force once you let it go is gravity acting down. You're neglecting air resistance here for now in these problems for this test. So for projectile motion situations, remember that the acceleration in the X direction is 0 because we're neglecting air resistance. And the acceleration in the Y direction is negative 9.8 meters per second squared, assuming that down is negative. Okay, and that's the Y acceleration. Okay, remember that if you have two-dimensional motion in X and in Y, then remember that X and Y motion are two separate and distinct sets of equations that are just linked by time. Remember that the Y equations dictate how long the object is in the air. So Y dictates the time of flight, okay? And remember that the X has no acceleration. So those are some important key ideas to remember. Be sure that you can solve kinematics problems, okay? We also talked about graphing motion and position, velocity, and acceleration versus time graphs. Remember that these things are related to one another graphically. The slope of the position versus time graph is going to be the velocity, right? The instantaneous velocity, because V is equal to dx dt. So the slope of the position versus time graph is the value on the velocity graph. The slope of the velocity graph is the value on the acceleration graph, because A is equal to dv dt, okay? Remember that on this position versus time graph, for example, here you see an object moving and the motion of the object is dictated by that orange or represented by that orange line there. So here the position is a maximum or a minimum at the turning point, okay? And at that turning point, the velocity is equal to 0. So for example, here you have an object that's moving from 30 meters and then it's traveling, say, to the right, okay, to X is equal to 50 meters. And then it turns around and starts going left. So it goes from 50 to 40 to 0 and so on and so forth. So remember that in one-dimensional motion, usually right is positive, up is positive, that kind of thing. So for example, given a common assumption, here we start to the right of the origin at X is equal to 30. We travel to the right to X is equal to 50 by 20 meters. Then we turn around or back up and we start traveling back towards the origin, moving left. So that's that deal, okay? Remember that at that maximum or minimum on the position versus time graph, the slope is 0 at B, okay? So that means that if the slope is 0, the velocity is 0. So when you turn around, you have to stop, even if it's just for a split second, right? Okay, so the tangent lines to the position versus time graph at the top of the curve right here, that's going to be a horizontal line. So the tangent line here would be horizontal. That means the slope is 0. So that means that the velocity is 0 at that point. So in these three graphs, you have the blue, the green, and the orange graph depicting the position, velocity, and the acceleration versus time. And you can see that at the same instant in time that you have a 0 slope on your position versus time graph, you have a value of 0 on your velocity versus time graph. Okay. All right. Now, the slope on the position versus time graph is going to be your velocity value. So since the slope is positive before our turning point, that means that the velocity is positive here. Remember that the direction of the velocity in a 1D graph is indicated by the sign. So let's say that we're traveling to the right and we've called to the right positive. That means that before the turning point, we're going to the right. Now we turn around and we start going to the left. That makes our slope for that position versus time graph negative. And you can see correspondingly that the values of the velocity are below the time axis here, okay? Now remember that if the magnitude of the velocity is getting lower, it's slowing down. And if the magnitude of the velocity is getting larger, it's speeding up. So from the initial point in time, t is equal to 0 to the turning point, the object, since the slope is getting shallower and shallower, is slowing down. So it starts off at a positive velocity and goes to 0 at the turning point. Then once it turns around, you can see that the magnitude of the velocity vector gets large again, okay? And that means it's speeding up. It's speeding up to the left, okay? So it's going to the left and getting faster and faster. Now, the velocity versus time graph here is a straight line, okay? That means that since the slope of the velocity is the acceleration, that the acceleration is a constant value here. The slope of the velocity versus time graph is negative, which means the acceleration is a negative acceleration, okay? So that's the deal. Make sure that you understand how to interpret these position versus time graphs, velocity versus time graphs, and acceleration. Okay, so if you have constant velocity motion in the column on the left, you have an acceleration of 0. You have a horizontal line on your velocity versus time graph, and you have a straight line on your position versus time graph. If you have a constant acceleration column here on the right, you have a horizontal line on your acceleration versus time graph. You have a straight line on your velocity versus time graph, and you have a parabolic line on your position versus time graph. Okay, so that's how that goes. Okay, moving on to a new topic. We talked about collisions and impulse, okay? Newton's second law is F is equal to dp dt. So if you have a finite time interval, delta p, then that means that you can write your force as the force is equal to delta p over delta t. And the F there will be the average force during that change in time, okay? Average force for a finite delta t. Taking that equation, you can multiply both sides by delta t, and then you have F times delta t is equal to delta p. This is the definition of the impulse. The impulse is the change in the momentum that something will experience, usually during a collision is when we talk about impulse. The force that the average force that object experiences during the collision will be that F average in the F delta t is equal to delta p equation, okay? Now, since the impulse is F delta t, the units are newtons times time, or newtons times seconds. Note that also from this F delta t is equal to delta p equation, we get our momentum update equation that we use in our code in Python. So if you've got delta p is equal to F delta t, then you can expand out your delta p as P final minus P initial, and then move that P initial to the other side. So P final is equal to P initial plus F net times delta t. And that's our momentum update equation that we use all the time in our code. Just go over here. Okay, spring force. Remember that Hooke's law gives us the force that a spring exerts on an object. If a spring is compressed or stretched, it just wants to return to its equilibrium position. The way that we write that is F is equal to minus Ks times L hat. Now, this is the notation that gets used in matter interaction. So let me redefine some things here. Note that it's more general notation than the one that you might have learned in your 1000 level class, because it can allow for motion in multiple dimensions. So here, the L vector stretches from the point of the attachment to the spring to the end there where the mass is attached. Okay, so the L vector points along the length of the spring. Here we're calling the unstretched length of the spring a scalar, L naught. Okay, so that's the unstretched or compressed length of the spring, L naught. Therefore, the stretch of the spring would be the magnitude of the vector L, which is the entire extension of the spring, the magnitude of that vector minus L naught. That's how much it's stretched or compressed. And then we can write Hooke's law as F is equal to minus Ks L hat. okay, where L hat is the unit vector that points along L, and minus Ks is the spring constant K, which is how stiff the spring is in newtons per meter, times how much it's stretched. So the force that a spring exerts is proportional to how far it is stretched or compressed, linearly proportional to how far it's stretched or compressed. And the force will always try to return the spring to the equilibrium position. Now, if you set this minus Ks L hat, if you take, for example, in one dimension, minus Kx is equal to ma, so that you set the Hooke's law force equal to Newton's second law of mass times acceleration. Remembering that the acceleration is the second order derivative time with respect to time of the position, d squared x dt squared, then you can solve that differential equation. The solution to the differential equation will give you the position versus time of the mass on the spring. So here, the solution to the motion of a mass on a spring in one dimension is the position with respect to time, x of t, is equal to a times cosine omega t plus phi. Here, a is the amplitude of oscillation, okay? It's the max displacement from equilibrium. Omega is the angular frequency, which is equal to the square root of k over m, the square root of the spring constant divided by the mass attached to the spring. And then phi is the phase constant. The phase constant is just an offset so that you don't always have to start your clock t is equal to 0 at the max compression or 0 displacement of the mass on a spring. Okay, you usually solve for phi given the initial conditions or the value of where the object is in its oscillation at a specific instant in time. Remember that the angular frequency is related to the regular frequency, which is the number of oscillations per second, via the equation omega is equal to 2 pi f, where f is the frequency in hertz or inverse seconds. That is also equal to 2 pi over the period big T. Okay, so remember the period is the amount of time that it takes to go through one full oscillation. Okay, so the period is the time it takes to go through one full oscillation. The frequency is the number of oscillations per second, which is hertz. And then the angular frequency is 2 pi times f. So that's how all those things relate to one another. Okay, Newton's law of universal gravitation. So all bodies with mass are attracted to other bodies with mass. The way that we say that mathematically is F is equal to negative big G times M1 times M2 over R squared times R hat. So the force exerted by body 1 on body 2, for example, is proportional to G, which is 6.673 times 10 to the minus 11 newtons times meter squared over kilogram squared. So that's the gravitational constant. I would give you that on a test, okay? M1 and M2 are the masses of objects 1 and 2 in kilograms. You multiply those times one another. And then you divide by the distance center to center between M1 and M2 squared. Okay, so that's the magnitude of the gravitational force. Remember that the direction of the gravitational force is attractive. So if you draw a line connecting the center of mass 1 to the center of mass 2, then the force will point towards the other object along that line. So you can see that the force on object 1 here points up and to the right, okay, because it's attracted to object 2. And object 2, the force on it points down and to the left towards object 1. Now, the way that you can calculate the gravitational force, you can just kind of turn a crank and use this method each and every time. First, you're going to calculate the displacement kind of between object 1 and object 2. So that's going to be R2 minus R1. So you subtract those two position vectors. Then you're going to calculate the magnitude of that vector, the magnitude of R, the distance between the two bodies center to center. Then you're going to calculate the magnitude of the force, which is the gravitational constant G times M1 times M2 divided by R squared. And then you'll calculate the direction by finding the unit vector R hat and taking the negative of it. And then you multiply the magnitude times that direction. That'll work every single time. Now, sometimes it's a little time consuming to find the unit vector, right? Because the unit vector is the vector divided by the square root of the sum of the squares of the components. Sometimes that takes a minute. If it helps you, if this is faster for you, then you can remember that the unit vector is equal to the vector divided by its magnitude, which means that you can write the force for Newton's law of universal gravitation the way that we just spoke about, negative G M1 M2 over R squared R hat. Or if it saves you time, negative g times m1 times m2 times the vector r divided by r cubed. That's okay too. So if that's faster for you, no problem, do that on the test, okay? If you have trouble with unit vectors especially. Okay, gravity near Earth's surface. Remember that we have the force due to gravity here on Earth's surface, the weight, mg, which you're probably familiar with from your 1000 level physics classes. That is because of the gravitational attraction between the bodies here on Earth and the planet Earth itself, which is governed by Newton's law of universal gravitation. So that means that you have to be able to set, for example, let's say that we're trying to calculate the weight of this person here, up here in Canada or whatever. So we're trying to calculate their weight mg. We could also say that we want to measure Earth's gravitational pull on the person. So we say big G, little m times the mass of the Earth divided by the radius of the Earth squared, all right? And that'll give us, little m's canceling out on both sides, G. And if you solve for that, you get 9.8 meters per second squared. So little m times little g would give you the same solution as Newton's law of universal gravitation, all right? That means that if you're at some height above Earth's surface, right, some distance h above Earth's surface, it can reduce the effective pull of gravity, reduce the acceleration due to gravity. It would reduce it by g is equal to g big me, mass of the Earth there, divided by the radius of the Earth plus h, quantity squared, okay? So g decreases with increasing altitude. And as you get infinitely far away, of course, your weight would go to 0 for the pull of Earth gravity. It also means that, you know, the acceleration on different planets or the moon or something like that can be different depending on what the radius and the mass of the planet is. All right, linear momentum, final concept. Whenever two or more particles are in an isolated system and they interact, the total momentum of the system remains constant if the sum of the external forces is 0, okay? Now, there can be internal forces. So for example, if body 1 and body 2 are traveling towards one another and collide and bounce off, okay? That collision force is internal to the system. And so if there's no external forces, you can say that momentum is conserved during collisions. So what that would look like, if you wrote it via Newton's second law, is F is equal to delta P over delta T would be equal to 0 because the external force, or F, is 0. And then that would mean that delta P is also 0. Okay, so the momentum of the system is conserved. Now that is the momentum of the system. As you can see, even just by my little simple example of the two bodies hitting one another and bouncing off, the momentum of either body, right, will change. This one goes like that, turns around and goes the other way, and this one goes like that, turns around and goes the other way. Their momenta have obviously changed, but the system's momentum remains the same, okay? Okay, so how would we do conservation momentum problems? First of all, you've got to find the total momentum of the system. So P total would be equal to, for example, for a two-body system, P1 plus P2. If you have more bodies, you just keep summing, okay? Now, that's going to be a constant. So P1 plus P2 initial has to equal P1 plus P2 final. What that means, too, is that it's going to be conserved via components, okay? So you can have, for example, three-dimensional motion, three separate equations, right? One for the x, one for the y, and one for the z components. And they have to be the same in each component. So P initial in the x equals P final in the x, P initial in the y equals P final in the y, and P initial in the z has to equal P final in the z, okay? So there you go. All right, finalmente, last thing. There's a special point in a system or an object called the center of mass. And you can see that that point will move as if all the mass of the system is concentrated at that point. If you have a system of individual little particles, the center of mass can be found by the R center of mass is 1 over the total mass, or big M here, times the sum of mi times ri, where mi is the mass of particle I and ri is the position coordinate for particle I. Remember that we define a position coordinate as, or position vector as the x coordinate I hat plus the y coordinate j hat plus the z coordinate k hat. So that's how we're defining it here. So if you're to then take the time derivative of the center of mass, then the V center of mass is dr center of mass dt. And so that would mean that for multiple bodies, plugging in for what our center of mass is, you've got m1 dr1 dt plus m2 dr2 dt, and so on and so forth, divided by the total mass, right? Well, dr1 dt is going to be the velocity of particle 1. So that's m1 v1 plus m2 v2 plus m3 v3, then divided by the total mass, okay? And so what this tells us is that if I multiply both sides of that equation by the total mass of the system, big M, then I have the mass, the momentum of the center of mass, which is the momentum of the system, right, equals to the mass times the velocity of the center of mass. So that's what we've got. And we had some problems, homework problems, that we went over on how to do those. Okay. That's it. That's the tobacco auctioneer tour of the topics that are going to be on the test. Now, this is a very broad brush, okay? If you were confused about anything that I said during any of these lectures, remember, you can always go back and watch in more depth on any one of the topics covered. Thanks for your time. Happy studying and good luck.